Now let's start with the cubic family. We are stepping into the world of x cubed, and I want you to be kind of like a detective for the next few minutes. Look at this graph. Let's start with y equal to x3. Notice that these are no longer parabola. The cubic function creates what we call the S shape, or we call it the sigmoid shape. They have this beautiful flowing quality, kind of like a gentle wave frozen in time. Now look at the next graph, 5x cubed. What do you notice about these two graphs? Both the curve fall from the bottom left to the top right, and both pass through the origin, and one is a lot steeper than the other. Can you see how the coefficient 5 affects the steepness? Now let's look at negative x cubed. Let's compare the first and third graph, x cubed versus negative x cubed. We notice that the negative sign has flipped the entire curve. Instead of flowing up from left to right, it's falling down. It's like looking at the first graph in a mirror placed horizontally. And finally, let's look at the next graph. This last graph is negative 5x cubed. It's kind of combined both effects. It's flipped like negative x cubed, but it's also stretched like 5x cubed. Here's what makes cubic kind of special. Unlike quadratic, they have one turning point. Cubic function can have up to even two turning points, creating this kind of complex wave-like behavior. They can model things like population growth that started slow, accelerate rapidly, and then level off. To summarize, these are the properties of cubic function. Every cubic function kind of creates this distinctive S shape we have to see. It's like a kind of like a mathematical signature. No matter how you modify the equation, the flowing S curve always emerges. And notice how every single one passes through the origin at 0, 0. This is not a coincidence because when x equal to 0, x cubed will always be 0. And look at the effect of positive coefficient. Look at x cubed versus 5x cubed. Both have that same elegant S shape falling from bottom left to top right. But the coefficient 5 acts like a stretching machine. It pulls the curve vertically, making it more steep and kind of look a bit more dramatic. The larger the positive coefficient, the more stretched and more steep your S curve become. And lastly, let's look at the power of negative coefficient. This is where the cubic functions show their personality. The negative sign acts like a flip switch, turning your S curve upside down. Instead of raising from left to right, it's now falling. And if we combine the negative with a larger coefficient like negative 5 x cubed, we get both of the effect, flip, and it's also steeper. Now try to do this yourself. Plot the following graph of y equal to 2x cubed. Notice how x cubed behave. At x equal to negative 1, we get x cubed equal to negative 1. At x equal to 0, we get x cubed equal to 0. X equal to 1, we get x cubed equal to 1. And then x equal to 2, we get x cubed equal to 8. Now for y equal to 2x cubed, you simply multiply each value of the x cubed value by 2. So we get negative 2 when x equal to negative 1. And then we have 0, 2, and 16. Once you verify this correlation, you can plot this point on your graph and then try to connect them with a smooth curve. You will see this distinctive, characteristic S shape that emerge. Notice how the curve is kind of flat near the origin, but then as x increases, it also shoots up dramatically. Now, let's start to go into this term called transformation. We start to figure out how we can move the cubic function around the coordinate plane. Let's start with what we know. Remember our basic cubic function, x cubed? They always pass through the origin at 0, 0. But let's do this with x cubed plus 2. Look at how the graph has changed. The plus 2 at the end has lifted the entire S curve upwards by exactly 2 units. The curve have the same shape, the same steepness, but it's kind of being moved. Instead of passing through 0, 0, it now passes through 0, 2. Now look at x cubed minus 2. Can you see that the negative 2 has pushed the entire curve downwards by 2 units? Same S shape, but now it passes through 0, negative 2. Now let's look at negative x cubed plus 2. Remember, the negative sign flip our S curve upside down, but then the plus 2 kind of moves the flip curve outwards. This is kind of called vertical translation, and it's incredibly powerful. Now lastly, for negative x cubed minus 2, remember that our S curve is now flipped, and then negative 2 bring it down vertically downwards. Let's summarize the pattern we have just seen. The first principle is that the constant kind of preserves the shape. Whether you add 2, minus 5, or add 100 to your cubic function, the S curve maintains the same shape and steepness. The constant is purely kind of like an elevator. It lifts or lowers your graph, but there is no stretching or squashing done. If you have a positive constant, it is kind of like elevator bringing your graph upwards. Every time you see a every time you see a plus 2, plus 5, or any positive number, think of how it's going to lift the entire graph upwards by that units. It's simple and predictable. On the other hand, negative constants are going to bring the entire graph downwards by that amount. To take note that the orders kind of matters, the negative sign in front of the SQ will flip the curve first, and then we do the vertical shifting. The order matters, we don't move and flip, we kind of flip first and we move. So for negative s cubed plus 2, we flip the S curve down upside down first, and then we lift it up by 2 units. Now let's spend some time to plot the graph 2x cubed minus 1. Here is the answer for the table. Please verify. Now let's look at the graph we draw. In fact, you should be able to predict how this graph looks like even before you plot the graph. You can see the mental image of y equal to 2x cubed, the steep S curve. It's kind of shifted downwards by 1 unit, so the curve now passes through 0, negative 1 instead of 0, 0. Notice how this curve still maintains the cubic shape. There's a steep growth on both ends and a small transition through the middle.
Smash your maths exams. Download Learn Maths Today for real exam questions and achieve top marks.